Hey guys, welcome to Elevated Systems. I'm your host CJ. A couple of months ago, I did a video on refurbishing a graphics card. In that video, I actually washed the card in my kitchen sink. Now, most people know that tap water conducts electricity. However, I've come to learn that many people believe that some liquids commonly used in computers are non-conductive. So today we're going to do a little myth busting. And like Mythbusters, at the end there might even be an explosion. But first, let's set things up. I have several liquids here that are commonly used on or in PCs. I got some cups to hold said liquids, and I have this digital multimeter to determine whether or not these liquids do in fact conduct electricity. And to do that, I'm going to measure the resistance of those liquids in ohms. Ohm. No, not that ohms. The unit of resistance named after this guy, Georg Ohm, who came up with Ohm's Law, which I'm not going to bore you with because thanks to modern technology, I don't have to do math. Simply by sticking these probes in our liquid sample, we'll get a reading of how much electrical resistance there is, if any. If the fluid is truly non-conductive, or at least not conductive enough to register on my meter, we'll just see this. OL, or open loop, which means the resistance is so great it exceeds the limit of the meter. Now, on the other hand, if any number shows up, that means there is indeed a current running through the fluid, meaning it does conduct electricity. The bigger the number, the less conductive. Now, to reduce some of the variables, I have each cup marked so we are measuring the same amount of each liquid. I've also taped my probes together so the distance between them is the same for each sample. And I have a bunch of these lint-free cloths to dry the probes off between each sample. So, let's just jump into it. And we're going to start with our controls. Now, these aren't true scientific controls, but I'll explain a true control at the end because I don't want to give anything away for the sake of the demonstration. I'm just going to use two liquids to demonstrate how our multimeter works measuring resistance in liquids. So starting with just plain tap water. So you can see we have a reading of somewhere around 0.6 to 0.7, which means there's a significant amount of resistance in this water. Now, I'm going to add about 1.5 grams of salt. Common table salt. All right, now I'll test this again. And now we can see we get a reading of 130 to, well, let it stabilize here. The salt is still dissolving into the water, but we're getting over 160 kiloohms or kilo ohms. A significantly smaller number, meaning that the salt water is more conductive. And this demonstrates how and why fluids are conductive. Now, pure water, just H2O, nothing else added, does not conduct electricity. It actually needs to contain dissolved solids or ions to carry that electrical charge. This is why our saltwater sample has much less resistance. There's a whole lot more ions carrying that current across the water between the probes. So that's why we use distilled water to cool our custom water-cooled PCs, because it's pure water, so therefore non-conductive, right? Well, let's see. So this gallon is actually brand new. I just bought it this morning, so let's pop it open. And let's see. There we go, 0.66 that's almost the same exact resistance, or the same exact resistance as our tap water. So my pure water is not really pure. It actually has about the same resistance as my tap water. That's a reading, so there is current moving between the probes, therefore distilled water is, however slight, conductive. So why have we all heard that it's not? Well, that's because of two problems with the distilling process for consumer grade distilled water. Really quick, distilled water is made by boiling regular tap water in most cases, and then collecting the steam, condensing it back into water, theoretically leaving all the contaminants and dissolved solids behind in the kettle. The first problem with this is that some of the contaminants have a lower boiling point than the water itself, so unless temperature steps are used to collect and remove these contaminants at their respective boiling points, or other methods are used later in the process, these contaminants are still present. The second problem is that the steam is usually collected and condensed in copper, brass, or stainless steel coils. Think bootlegging still. Those coils can transfer some of these ions to the water, but most commonly, the ions are just simply reabsorbed from the atmosphere, and hence a conductive fluid. So, what about something like this? EK cryofuel. I mean, this is made specifically to go into a computer, right? It's gotta be non-conductive. And honestly, I don't know, but I suspect because of the anti-corrosion and antimicrobial additives, it will probably carry a charge, but let's find out. All right, here we go. And it is about the same or even more conductive than our distilled water. So these are a couple examples of liquids we put into our custom cooled PCs. What about something like this? Isopropyl alcohol. We use this all the time to clean thermal paste, right? Because, well, it works and it's non-conductive, right? So if a bit gets down into the CPU socket, it's no big deal. Well, let's see. I actually have two concentrations, 70% and 99%. Depending where you are, you can find one or both of these in your local supermarket or drugstore. There's also 90 or 91% bottles out there. We'll start with the 70% solution. So, like pure water, pure alcohol is also not conductive. However, this one is still 30% this, water. So, I suspect if I can get it open. So, I suspect I'll get a slight reading from this. And let's see. Yeah, so now I'm getting a reading. So now we're up to almost 5, up to over 4, between 4 and 5 microohms, which is a significantly higher reading than our water. So although it's less conductive, it still does carry a charge. So let's see about our 99%. Now, in some locations, you can't actually buy 99% rubbing alcohol, and 91% is the best you can get in the consumer market. However, I can, so I'm going to test it. Now, unlike the 70% solution, the manufacturer doesn't add 1% water to make this a 99% solution. Because this is a consumer product, the manufacturing process isn't as strict, and basically it's labeled 99% because they just can't certify it as 100% pure without any contamination, so they give themselves a 1% buffer basically. So my prediction here is, because of the probability of something other than just alcohol in here, that it's ever so slightly conductive. However, I don't think my multimeter is sensitive enough to detect it. And wow, I was wrong. I actually have a reading of 0.4 micron. So that's a significant amount of resistance, but still a current. So even our 99% isopropyl alcohol is conductive. So those are our consumer grade products that are supposedly non-conductive, but as we saw, they are. So just to prove that these liquids, water and isopropyl alcohol, are in fact non-conductive in their pure forms, let's move on to our laboratory grade products, starting with the alcohol. Now, this is 99.9% isopropyl alcohol. The manufacturing process here is more strict, so they only need a 0.1% buffer. So let's give this one a shot. And there we go. Finally, no reading, no current, non-conductive. Okay, let's move on to our pure water. Now, the difference between this deionized water and the distilled water is that not only is this water filtered down to like 0.2 microns, it's then filtered through a special resin that completely removes all the ions from the water. It is then kept in a vacuum or blanketed with nitrogen, so it can't even reabsorb ions from the atmosphere. So we have 100% pure H2O. All right. Hopefully we can see those water molecules with those tight covalent bonds not carrying a charge. So pure water is in fact non-conductive. Not pure, not pure, not pure, conductive, pure, not conductive. So this would in fact be used as our negative control at the beginning of the experiment, but that would have spoiled the ending. But this isn't the ending. I promised the possibility of explosions. How confident am I that this bottle of water is in fact non-conductive? Well, that's the fun part of the experiment. I'm going to pour this entire bottle onto a powered and running computer. So, here we go. Hell no, I'm not doing that. That's my $6,000 production workstation, which, yes, is just sitting here on an open air test bench, and I will actually be putting this back into a case relatively soon. That video will be coming up, so make sure you get subscribed for that. But for this demonstration, I'll be pouring water onto a slightly less expensive and very bare bones, but still fully powered and running computer. This is a Core i5-7400 on a MSI B250M Bazooka motherboard and one 8GB stick of RAM, just enough to get it to post into BIOS. So let me get this system into a container and all hooked up and powered on. Okay, everything's ready. The system's powered on. I'm in the BIOS menu. Now, if everything goes dark, that's a fail because my lights are actually on the same circuit as this computer. In fact, my front camera is actually on the same circuit. So if I fry this board and blow a breaker, we'll know right away. And Oh, well. I'd say that's a fail. You shut it down. I don't want to press my luck. Okay. I fried this system. Definitely a fail. But why? Well, what I expected to happen did in fact happen. It just happened faster than I expected it to. But let's confirm. I'll just pour this water into one of our cups. Now grab my multimeter here and let's take a reading. And yeah, see, look, we have current. So here's what happened. Water is the universal solvent. It doesn't stay pure for long. As soon as I opened this bottle, it began absorbing ions, and when I poured it on this old motherboard, it started dissolving all the stuff on the board, and all that stuff is now dissolved solids and ions in the water. Our deionized water is now ionized. And as I just demonstrated, it just takes the slightest degree of conductivity to short out a computer. That's also the reason you don't need to use deionized water in your cooling loop instead of distilled water. First off, this 1 liter of deionized water cost almost 20 bucks. The gallon of distilled water was less than 2. And like I said, as soon as I opened this bottle, the water started absorbing ions from the air. If you add it to a cooling loop, it's just going to pick up all that stuff from circulating around the metal components and become just as conductive, even more so than, well, this motherboard water. So, what was the point of all this? Just to have some fun? Well, for me, yeah, kinda. But really, it was like I said in the beginning, to bust some myths. I actually saw another YouTube, who will remain nameless, explain in a video that his open loop leaked into his system and may have gotten into his power supply. But it was okay. He used distilled water, so it was non-conductive and would just evaporate out. So maybe he'll see this and be educated like you are now. But that's it for this one, guys. I got some hardware to dry out and see if I can salvage. I hope you learned something. That's always my goal. If you like this video, please hit that like icon on the way out. And as always, the best way to support a small channel like mine is by subscribing and maybe checking out some of my other stuff. I hope to see you for the next one. Until then, I'm CJ. You have a great week.